Hello class, I want to have a short video to go over the excess and partial molar properties. So the title is excess partial properties. So those would be the calculations we discussed from lecture 17 to 19. If you need, please go and review those slides as well. Let's try to recall what we discussed for gas. We say for gas, in order to see the difference between real and ideal, we define this as a residual property. Residual property. For the property of M, the residual property is defined as property under this realistic temperature and pressure. We try to imagine that we are going to have the same ideal behavior at this same temperature and pressure. In general, we are interested M is volume, N is entropy, N is the four energy equations: internal energy, H, A, and Gibbs energy. So that is for the gas. And I hope you still recall that in order to do the calculation, we try to set up the connection. Now this is the ideal gas behavior at this high temperature and pressure. We try to always compare this with the real ideal, which is the actual ideal gas behavior at this same temperature, but we are looking at this low pressure P0. So for the available data, we say as long as P0 is low, then this should be a good justification of the actual ideal gas behavior. So the reason why we are interested in this state is we know the data. Now the question is, in order to calculate this MR, we try to evaluate the difference between the M actual versus the imagined ideal gas behavior at this high temperature pressure, and we also connect the actual ideal gas behavior at a high temperature but low pressure P0 at 1 atm. So essentially we are looking at this ideal gas behavior. So ideal gas property change. Which is from at this fixed temperature T, pressure goes from P0 to whatever high pressure you are interested in. And then for any property of this N, if we are trying to recall, we express this N as a temperature and pressure dependence, then from there it is still the ideal gas. Try to remind us. And from there we say, hey, I want to evaluate the difference due to the pressure change P0 to P. Then in order to calculate the change, then we better have the general equation. Say this is the fourth derivative of that property M is partial derivative of N over dt at fixed pressure dt plus partial derivative of m with respect to pressure change at fixed temperature dp. So from there we say, since temperature is fixed, dt goes 0. Therefore, we would have dn would be basically this correlation, right? Then you just need to evaluate that dn of this p naught from p. What is this partial derivative of m with respect to pressure at fixed temperature dp? What is this p naught from p? So we can calculate the residual property. Like we discussed in the past. So now for the liquid, we have another property. This is residual property. For the liquid, we have another property, which is the excess property. By definition, the excess property is defined as for the same quantity, volume, entropy, internal energy, enthalpy, Helmholtz energy, and Gibbs energy. The excess property would be defined as m T and P minus still the same ideal solution. So there, this is the ideal solution for liquids. Then the trouble is that we don't have the quite nice equation of state to calculate or to estimate the property for this ideal solution condition. However, we do have other ways to understand the general model. So in order to have that, we need to look at general equations for ideal solution, which is discussed, I believe, in chapter 10 from page 384, where we have a list of equations for the ideal solution. So if I start with the volume, then I would have the volume for the ideal solution will be the summation of all the components in the liquid phase times their pure. So this is the pure volume for component I. And we also have this enthalpy is for the ideal solution is also the summation of xi times hi. However, the entropy and the Gibbs energy, they are complicated for the ideal solution. Let's say this is ideal solution. For the entropy, the entropy of the ideal solution state will be summation of xi, si of the pure component, minus r summation of xi log xi. Okay. Lastly, this would be the ideal Gibbs energy will be summation of xi times the corresponding component, pure component, gi plus rt xi log xi. So the four equations coming from this chapter 4, page 384. So now suppose we have access to the four equations, then when we look at the axis is defined as the difference between the actual of the mixture minus the imaginary ideal solution, then we need to figure out what is the actual TP. Keep that in mind. This is my mixture. Of liquid. So this is, I hope you still recall, this is a summation of xi partial molar property of Mi. What is that Mi? Mi is defined as d of the total over that component Ni, while evaluated at Tp and J, they are fixed. Okay, so hope to recall this is the partial molar property. Alright, so now coming back to the excess property calculation, we could rewrite this as the excess property is n Tp minus m ideal solution of Tp. So if we try to take a look at so let's start with the excess Gibbs. For excess Gibbs, that is defined as GTP of the mixture minus G of the ideal TP. So we can, for the mixture, try to remind us, this is the mixture. Then we would have xi gi partial, right? This is the first term. The second term is that I have over here is xi gi plus rt summation xi log xi. Alright, so if I'm trying to reorganize these three terms, this is xi gi minus xi gi. Now this is a minus rt summation xi log xi. So I hope you realize this is delta G. Okay, and I still have this RT xi log xi. So this is why we are receiving this general note. So we try to convert or try to correlate the excess Gibbs integer with respect to this mixing. This is mixing property. Okay, and if you want to look at the excess HP, then we can do the almost the same. This is S TP minus S ideal solution TP. This is S TP minus xi, the pure component, minus R summation xi log xi. Try to rearrange the first two terms, STP, with a mixture minus xi over the corresponding pure component. Try to put them together, plus R summation xi log xi. That would be delta S plus R xi log xi. Okay. For this enthalpy for excess, which is H minus H ideal. So now we use the equation that is just delta H. For the volume, ideal solution TMP, that is V TP minus xi Vi, which is delta V. Okay. So still the message is SE, the excess property of entropy, is somehow related with delta S. The excess enthalpy is also related with delta H. It's actually exactly the same. Okay. For the excess volume, the R also the same. Right? So this is the first information we can have, and then the equations we've discussed on these slides would be, I hope you realize that this SE is not delta S, GE is not delta G. So if we put them together, GE is RT delta G is for the general case, SE would be delta S. Yes. Alright. So the general information is if we want to calculate the excess property, we try to connect that with the mixing property of M. For that mixing, I need to calculate the partial, and I'd better understand the pure, and I can go from there to finish all my calculations. This the one equation we discussed would be M is also the total would be A minus, for a binary system, would it be A minus x1 and 1 plus x2 and 2. So they are the pure. Then we can go M of the mixture would be x1 and 1 partial plus x2 and 2 partial minus x1 and 1 x2 and 2. So they are partial. This is one useful equation. The other would be we discussed that for the partial molar property, if this is my total, this would be summation of mi times mi partial. From that equation, if we divide on both sides by m, this is mi over total number of mole, mi partial, which is xi mi partial. Okay. Equation C is we call this as how to correlate two components out of a binary system. That is, m1 partial is total minus the other component x2 dm over dx2, keeping temperature and pressure fixed. So I'm trying to have your attention. This is 1, this is 2, this is 2. But of course we know x1 plus x2 is 1, so that x2 is 1 minus x1, so that dx2 would be negative dx1. Okay? So using those information, we try to modify that equation slightly. Firstly, we try to replace dx2 by dx1, then this is m minus x2 dn over dx1 tp. This is x1, then this should be plus. Okay. Secondly, if I want to replace this x2 by 1 minus x1, then I have dn over dx1, still keeping same temperature, pressure fixed. So this is m1 partial, this is also m1 partial. Try to pay attention to those. You don't have to memorize the equations and provided one equation, but you have to know how to move from one equation to the other needed different forms. The fourth useful equation is coming from this two extremes. I hope you still recall this property at dilute, which is x1 goes 0 for m1 partial. That will give us m1 partial at dilute. Okay. The other is, of course, if I'm going to push x1 goes to 1 for the same partial molar property, this shall be my pure. This is pure. Alright. The other useful equation would be the pair of log activity coefficient with excess Gibbs energy of RT. So they are the pair of partial molar property, which is we can have the like we did in the useful equation C. If I have a binary system, this is activity coefficient 1 is the total. Total is GE over RT minus the other x2 times partial derivative of total GE over RT over dx2, keeping temperature and pressure fixed. Okay. And then the equation, useful equation F, would be the so-called GD equation, Gibbs to Hammer equation. That equation would tell us that if you are going to have still, let's use the binary equation as the example, then you would have generally is xi dmi partial would be 0. So for a binary system, this is x1 dm1 partial plus x2 dm2 partial will be 0. So sometimes we have a different form of the Gibbs to Hammer equation. One is we move component to the other side of the equation. Okay, this is the one. The second is we try to use this this dx1 is negative dx2. So if we try to divide on both sides by dx2, then I would have dx1 dm1 1 partial dx1 will be negative x2 dm2 partial is dx1. Okay, which is x1 dm1 partial dx1. Now this is x2 dm2 partial of dx2. Pay attention to the negative sign, negative sign. There's no negative sign, but I'm using a good symmetry. This is a positive sign. I have this useful equation. I believe the last year's discussions we had, so now in order to use most likely the liquid phase for the activity coefficient, we need to figure out some correlation of log gamma I is a function of x1 and x2. Right? Call this as a function. Like Van Laar equation and all other development, and we can go from there. So this is the general equations or the discussions we have had. So now let's try to look at 2 examples from the previous exams. Number 1 is I need to insert. So now let's take a look at examples. First example is I believe this is problem 4 of 2015, last year. We had a problem in this area. So let's try to insert this. Right here. Alright, make this a little bit larger. Okay. So the problem statement says having a vapor-liquid equilibrium, component 1, component 2 at this known. This is a known temperature. Fixed, and the excess Gibbs energy can expressed as GE over RT is the product of x1 and x2. It's a coefficient 2.2, and it says the activity coefficient model will be this log gamma 1, log gamma 2. Now the question is it possible to have the azeotrope of the mixture at 80 degrees C? If so, what is the pressure at the azeotrope? What is the composition of vapor phase Y1 and Y2 at that azeotrope? Number 1 is, what is that azeotrope? Azeotrope simply says x1 same as y1, and of course we are going to have 1 minus x1 is 1 minus y1, which is x2 is the same as y2. Okay, so eventually we have to satisfy that equation in order to run the calculation. And then the vapor-liquid equilibrium, in general we have to satisfy this. If this is VLE, T1 is T2, which is known. P1 is also P2, where we only have one single vapor phase, and then we have to have this F vapor should be the F liquid, and if we look at the vapor phase as well as the liquid phase, then in general we are looking at this if you guess it, the coefficient phi I times yi of the total pressure will be the exact same as activity coefficient xi pi set. I is that two components. Okay, so that is the very general VLE equation we have to satisfy in order to achieve the equilibrium in the first place. And then the known condition is we need to satisfy x1 is y1, x2 is y2. This is number. This is the provided information. And looks like we have activity coefficient is provided. So that further confirms that we need to worry about that activity coefficient for the liquid phase. For the PI set, we have the two Antonio equations, so that we shall be able to figure out y1 would be same as x1. P total is coming from the two components, so we can figure out. But what is this one? What is activity? What is fugacity coefficient? Okay. So in order to see what the fugacity coefficient is, then we need to think about whether we have to worry about it. So then we need to take a look at this total, P total. Is it a small value, or it should be a high pressure that we need to worry about the fugacity coefficient? How can we do that? Well, the vapor phase is coming from the two components. So let's try to evaluate their saturation pressure one by one at this known temperature. So we know the temperature is 80 degrees. From there we can calculate P1 set using the Antonio equation, and I have the values in the shared solution, which is 108.34 kPa. Similarly, we can easily solve for P2 set. That is 19.76 kPa. So from there we can see that P shall go between P2 set, P1 set, generally around 180 or below 180. So this is the understanding that we are having this low pressure VLE, vapor liquid equilibrium, right? That is why all the activity, fugacity coefficient should be 1, and we are happy to stay with. So now if this is the case, then from the general equation, phi I yi p is gamma I xi pi set. So we can have the simplified form, which is for component 1, this is py1. I'm going to have x1 activity coefficient 1 p1 set, and I'm going to have the same equation for component 2, x2 gamma 2 p2 set. Okay. So now I'm having x1 is the same as y1, x2 is the same as I2. So moving forward, I can replace or simplify this as P of the total is gamma 1 P1 set, again P of the total 2 P2 set. Okay, which is like I did in the solution. If I take log on both sides, then I would have log P1 set will be log activity coefficient to log P2 set. Okay, now I have all those values. I know this is 2.2 x2 square. That is a known value. This is 2.2 x1 square, which is 2.2 1 minus x2 square, and I have this figured out. So I can do this as the equation of x2, and I solve for x2. The solution, if I have the right value, then x2 we can easily solve. This is x2, and then I know x1, and of course I know the corresponding y2. This is the corresponding y1. Alright. In order to have the p of the total, then as we have over here, we can pick up any equation for component 1 or component 2. This is activity coefficient p1 set, and we can evaluate their values. So that is the first question we have had in last year. The other example, take a look at this, is example 2. I believe this is the old problem 3 of 2016. Let's try to have the problem. Okay, so you have this problem still as a general access property calculation, and we also want to calculate a few extreme activity coefficient and dilute. So the problem says we have this excess Gibbs energy for liquid argon and methane mixture as a function of their corresponding compositions. A, B are constants depending on temperature. For the temperature range from 109 Kelvin to 116 Kelvin, A, B have been fit to the experiment data, and we have this correlation. So now the first is we need to derive expression for activity coefficient for argon and the methane. The second is calculate this activity coefficient argon, methane. Second is to calculate this activity coefficient at this known temperature and then a fixed composition. Third is to push to the limits to understand the dilute. So in order to calculate activity coefficient, we need to understand what is the equation we could have, and the provided equation is in terms of the Gibbs excess property. So there we quickly recall that if I have this log activity coefficient of argon, that should be this GE of RT minus X of the methane times the partial derivative of GE over RT with respect to X methane. Right? Of course, temperature and pressure, they are fixed. So if I know that, then GE over RT is expressed as X argon methane A minus B times 1 minus 2x argon. So in order to take the partial derivative with respect to x methane, then here I'm trying to rearrange the terms, trying to get rid of all those argon terms. So this is 1 minus x methane times x methane. A, B are only depending on temperature. So when I take this partial derivative, that would be 0. B 1 minus 2 times 1 minus okay. Then you just simplify this term as a function of XCH4. Okay. Then you take then you can solve for GE over RT with respect to XCH4. Then you can have the problem solved. And then in order to figure out, so this would be part A. Then the other is, well, I can do this very similarly. I can write down this activity coefficient for methane. Shall be excess Gibbs energy of RT minus X argon times partial derivative excess Gibbs energy of RT d X argon, temperature, pressure fixed. So you see this is argon, and then I do the calculations where I'm trying to rewrite G of RT now as a function of X argon. Right, this is number 1. The other possible way is I know the activity coefficient of argon. I'll be calculating argon. Yes, okay. We finished the calculation of activity coefficient of argon, so that I know X of argon times D log coefficient argon plus X of methane D log coefficient of methane should be 0. This is coming from GT equation. Okay. So in theory, you are able to solve this question because we know this argon. We have this figured out. This is basically 1 minus X argon, and we should be able to write this D log CH4 would be a function of argon d X argon somehow, right? I don't have the exact format. If you decide to use this as the procedure, you need to be careful when you run this. let's say this is x argon, dx argon. So you have to worry about all those terms. Okay. When you have to run the integral, then you have to decide from what value all the way up to the interested value. So there I'm going to put a big question mark over here and try to check the slides examples I have. Okay. So this is for the first part. For part B, once we have those values, that should be straightforward. For part B, if I know the temperature is 110 Kelvin, X argon is 0.3, then I can calculate all sorts of values. I can calculate A at this 110 Kelvin, can calculate B at 110 Kelvin. I can also calculate this activity coefficient of argon, and eventually the actual value of this argon. So that should be no problem at all. Part C. Part C is asking us to evaluate what is the activity coefficient argon at this 110 Kelvin. So in order to calculate that, we need to look at the solved log activity coefficient of argon in part A. So I'm copying this from the solution. This is negative 4b x to the cube CH4 plus a plus 3b x to the square CH4. So in order to calculate this, we have to push this to the limit of 0. Then this is named as AR of argon at dilute, right? So in order to do that, we just use X argon is 0, well X methane is 1. Then we put this back to have this log a activity coefficient of argon will be negative 4b, this is 1, plus a plus 3b. Right? This is essentially a minus b. And if we know the temperature, then at this T is 100 Kelvin, then we can calculate the actual value of a minus b is 0.3205.